All right, so yeah, hello everyone. My name is Alex Moat. I'm presenting some work that I did this summer with Colby Franck from UC Santa Barbara and Milan, who we've all met at this point, looking at a neural network surrogate model for non-local thermal flux calculations. So some motivation behind this, the big break-even fusion reaction that was done at NIF in December was a huge development in the scientific community. And they managed to do it despite the fact that they only consumed about 4% of the fuel in the chamber. So our sort of question is how do we help them achieve the sort of 20% goal that they have sort of internally, or so I've been told. And one of the main ways of doing this is increasing the fidelity of the simulations that they use to sort of model their experiments, change their inputs, and really get the most out of these experiments before they actually do a shot. And specifically, we'd like to do that without increasing the amount of time that these simulations take, which is, sort of like having your cake and eating it too, right? These calculations are obviously very computationally expensive. For example, the sort of non-local Rad-Hydro equations that we're looking at, a kinetic solver can solve them, but it takes about 10 to the 12 operations for it to do these calculations. Whereas if you're looking at a neural network, you can get an approximation out as much as 1,000,000 times faster in 10 to the 6 operations. So our question was, can we build a neural network that can give us accurate predictions for these models? And it turns out we can to an extent. So we constructed a data set of MFEM simulations. Milan built a kinetic solver that did a sort of reduced version of the problem, so not the full 7D phase space, just a 1D, 2V phase space in the general SN branch of MFEM. We used third order approximation, and we swept over temperature parameters. We used a tool called Merlin to essentially do a parameter sweep over some different temperature inputs. And we designed a feed-forward neural network to take those values and give us outputs of predicted thermal flux. We wanted to capture the non-local information that's sort of necessary for these calculations. So we used a sort of shifting window to capture multiple neighboring input elements for each output prediction. So we would grab some elements to the left, some elements to the right in order to help do the prediction in the middle. Overall, the model reported 99.3% accuracy across the entire testing set, which we were quite pleased with. We can see some examples here on the bottom of the screen. And as the problem gets more non-local, so as the maximum temperature increases and the slope gets steeper, we actually see our model tends to give us a better fit. So as the problem gets harder to solve in kinetics, it gets easier for the model to deal with, which was.
2 minutes, it's up.
Thank you. So we have these results. What can we do with them? What can we do with these predictions? One application is sort of evolving the temperature in these problems over time. So we took an MFEM example 16 that is a sort of time evolution of temperature, and we modified the sort of equation that it was solving to a more complex version that has this sort of exponential beta term, as well as capturing the non-local thermal flux in that alpha term in the front. And using our neural network predictions, we can more quickly approximate that non-local alpha. We actually retrain the network on a more sort of refined set of simulations and actually increase the number of simulations. And we can see that this neural network adjusted alpha demonstrates improved temperature smoothing, which is sort of what we would expect flux values. And if we extend it all the way out to the end of our sort of time step, this is what we see: the initial temperature in black, the neural network adjusted alpha values in blue, and the constant alpha in orange. So we get a much smoother temperature evolution over time.
1 minute.
Thank you. Yeah, so there's a lot on this slide, and I won't go over all of it. The main sort of takeaway in terms of future development is that as we add more things to the model, which is what we would like to do. We'd like to build it up to the full, 7-dimensional version of the problem. We'd like it to solve more moments of the distribution functions, so not just thermal flux, but things like electric field. We're going to need deeper architectures. We used the feed-forward neural network for this, which worked great as a proof of concept. But we're gonna need to look at some deeper networks. And actually, Colby had some very promising results with a graph neural network that included some things like mean free path information on the edges that connect those elements. And we were able to get good results, not just on thermal flux, but also on electric field. So there's a lot of space for this model to grow and develop and sort of get more complex. But yeah, thank you very much for your time. I'm happy to take any questions at the end of the block or answer questions on Slack. Thanks very much.
My name is Amit Rotem. I'm a PhD student at Virginia Tech. I'm presenting the GPU acceleration of the interior penalty DG method, now implemented in MFEM. And I worked on this with Will Patzner as well as my advisor, Daniel Appello. Okay, so this is the bilinear form of the interior penalty DG method. Essentially, this is like the diffusion bilinear form in MFEM. And so what was already present was a partial assembly form of the volume term, but there wasn't a partial assembly form of the trace terms, which is kind of what makes this a DG rather than a continuous Galerkin finite element method. And so I'm particularly interested in using this because I am studying the Waveholtz algorithm, which essentially simulates Helmholtz equation by solving the wave equation multiple times. And so really the efficiency of that algorithm depends on how efficiently you can solve the wave equation. And so if we can implement this in a very fast way, namely using the partial assembly operators, we're on GPU, we're going to get a faster Helmholtz solve using this Waveholtz algorithm. So that was the goal of putting this into MFEM for me. And so here's what I'm going to present the results of the speed up of that implementation. Okay, so the kind of benchmark example is this. So we're going to measure the cost of applying this operator. We have this 3D mesh, which is, I can get into the specifications of that during the questions, I guess, as to why this specific mesh, but we're going to look at second order and fourth order elements, and we're going to compare the partial assembly and the full assembly, both in the MPI version and on the GPU. So for the full assembly is what we have on the left. We're going to use the 32 cores of like using MPI 32 cores is kind of the baseline speed. And we're going to first look at, so for second order elements, we see, okay, we get kind of a typical speed up with the full assembly, but then when we put it on the GPU with partial assembly, it's now about 17 times faster. And so on the GPU, this is like equivalent of being worth about 500 cores if we make a one-to-one comparison. And then on fourth order elements, we have an even more substantial speed up. So going from 32 cores of the full assembly and then going to GPU with partial assembly, we get a 400 times speed up relative to the 32 cores. So it's about the value of 10,000 cores, which is more than twice as many cores as there actually are on this GPU. And so there's clearly some merit to this, to using the partial assembly, especially on the GPU. If we compare just the partial assembly implementation with MPI to the GPU, we see something comparative, but of course not so substantial. So baseline again is 32 cores. On the GPU, it's about 16 times faster, so about the same as the speed up for full assembly. And then for fourth order elements, we still get a 20 times speed up. So it's still a substantial speed up to just using MPI. And then finally, I want to show kind of a one-to-one comparison of partial assembly versus full assembly. So the first, again, second order and fourth order elements. For the second order elements, we have that with if the 128 cores full assembly is the baseline, the partial assembly for second order elements is about comparable, 1.2 times faster, but on the GPU, it's about 5 times faster. And then for fourth order elements, we see a very substantial difference. So even without GPUs, just using the partial assembly is about times faster. And then using the GPU, it is about 45 times faster. Okay, thank you.
Hello, my name is Josiah. I am a Relogic research intern, and I will be kind of going over an update on the Project Minerva. So just kind of a refresher of what this project's goal is. It is to use programs like FEMAT, Abaqus, HyperMesh, and to use those to model meshes for MFIM, to kind of use their their mature commercial capabilities, making CAD programs pretty easily. So just kind of the update of the project is that there's a C++ code that has been created that takes Abaqus input files and HyperMesh input files and outputs a .mesh file and a .cpp file of a filled out MFIM model. We're hoping to get a FEMAT by the end of 2023 to get that also included. Right now, the program can take a input file that has text and hex, continuous mesh. Also, it can do surface loads like pressure and traction. It can do multiple isentropic materials. So this kind of whole program is supposed to help the user friendliness aspect of creating a mesh for MFIM. Relogic, so we're going to also create a website to host this kind of program so that people can use it. Just kind of a demonstration of possibly what could be used for. I've created a demo how to use this program. Once this is finished, this demo will be released on Relogic's website, and it will go over on how to make a Abaqus mesh, a HyperMesh, and hopefully by the end of 2023, a FEMAT mesh. Because there is a particular way that you have to create it in Abaqus and HyperMesh for MFIM to use it. Here's kind of an example. That's a simple rocket nozzle with internal pressure. So I just made it in HyperMesh and exported the .input file, ran the program, and it spat out a .cpp file and a .mesh file, and compiled the C++ program, and it outputted a pair of UVI, which you can see on the right of the screen. So just kind of to clarify, the main goal of this program is to make it so that it's more user-friendly for to use MFIM. And we're creating a web-based front end, and here's kind of a preview of what it's going to look like. Hopefully we'll have it finished by the end of 2023, probably will. You drop in your input file, it outputs a mesh and C++ file that you can use. And we'll also release the tutorials by then. And that is the end of my slides.
So my name is Mike Pozolp. I work at Lawrence Livermore, and I'm a fourth-year PhD student at UC Berkeley. Last year, a fellow student in my PhD program named Sam Olivier graduated and wrote a dissertation in which Olivier derived a collection of finite element discretizations and implemented them in MFIM. The discretizations are for a moment system that come from taking angular moments of a neutral particle Boltzmann transport equation. That Boltzmann equation is high dimensional. So in addition to the the 3 space and 1 time dimensions, so the 4 dimensions that we are typically familiar with, it also has angle and energy dependence. So that's how we get up to 7D. And the moment system is angle integrated, so it's only 5D instead of 7D. And in the method, at each iteration, Olivier used a deterministic method to solve the high dimensional equation and computed a closure that appears on the right-hand side as a source term for the low dimensional moment system. In the moment system that I'm investigating, it is a source term for a diffusion problem. So the left-hand side is a Laplacian, and I'll show these equations shortly. I have results based on a year of investigation in which, instead of using a deterministic method for the high dimensional problem, I chose to use a stochastic method, namely Monte Carlo. In these 7-dimensional problems, Monte Carlo avoids some non-physical negativities that can arise from conventional deterministic methods for solving the Boltzmann equation. And also it avoids discretization errors, which don't appear because Monte Carlo particles are not discretizing the 7D phase space. The problem that Monte Carlo introduces is it puts noise into this iteration. And this noise has degraded my convergence in the code that I've written for 1D and 2D results that I'm presenting here, in which I've typed out a finite difference discretization of the moment system. And in this next year of investigation, I intend to switch to a finite element discretization and look at a couple other ideas. So on the left-hand side, where it says the hybrid moment method, equations 1 are the high dimensional Boltzmann neutral particle transport equation. So it's a linear equation in 7 dimensions, reduced here, so steady state with energy dependence neglected. Equations 2 is the moment system. And then 3 is the moment system with one of the quantities eliminated. And the boxed term is the noisy quantity. So T is the noisy closure from my Monte Carlo solve, and it's twice differentiated. So I'm amplifying the noise through differentiation. In 1D, if we look at the results, the top 2 plots, that seems okay. Thanks, Milan. I'm observing the hypothesized convergence order, but in 2D, if we look at the plot on the bottom right, and the reason there's 2 plots for 1D and 2 plots for 2D is because my error has a term that depends on n, which is the number of Monte Carlo particles that I'm running, and h, the element width. So in 2D, I'm converging, but degraded with respect to my hypothesized linear convergence order. So I think noise is causing the problem. The 3 ideas I have for fixing this are: 1, switching to a finite element discretization and reusing Olivier's MFEM implementations. So if we look at that box term in equation 3, that'll offload one of the derivatives to a test function. Idea number 2 is to move the second derivative up into the Monte Carlo solve. So solving for div t instead of t. And then idea number 3 is a variance reduction scheme, which is a conventional method for reducing noise in Monte Carlo solutions, which will dampen the noise in t itself. That's it.
Yep, time is up. Thank you, Mike. It was a little alternative lightning talk, but you like it. The MFM community is friendly, and we want people to show us their research and results. So now it's time for questions. So anyone, please go ahead and ask with respect to the last 4 talks.
I have a question for Amit.
Yes, please.
So Amit, can you say a few words about the picture that you have on your title and last slides?
Sure thing. I can share my screen again to show that. So this is the one you're talking about, or the first one? They're kind of the same, yeah. But
Yeah.
yeah. So
Okay.
this problem is like taking. So if you've heard of the unilluminable room problem, it's essentially where you have you want to create some geometry where if you put which represents a room, where if you put a light source somewhere in that room, there will be a region in that room where there's no light source. And so this is kind of in the case where you do ray tracing, you can find such a solution. But when you have actual light, it tends to refract. And so we don't really get that. And so this is kind of part of like a study to investigate how unilluminable is the unilluminable room. And so this is kind of, we tried to extend that to 3 dimensions by taking the 2-dimensional problem and just rotating it. And it proves to be not very unilluminable. It looks very illuminated to me, at least in this frequency, at least for this range of frequencies that we've looked at.
Cool stuff.
I have a follow-up question. Can you go back a few slides when you showed the speed up with regard to, GPU? Oh, no, go further, maybe 2 slides back.
This one?
Yeah. So is this a single device or multiple devices?
This is a single device.
Okay, so you have one CPU which is connected to a single GPU?
Yes.
Okay. Now, the other thing is, I think you're showing some with the MPI, right? Some slides.
Yeah. So all of these, so we have here 32 cores, 64 cores, and 128 cores, all with MPI, and then also a single V100.
Oh, so you are not talking about MPI talking between different nodes, rather than you're talking about MPI within a single CPU. Is that what you were talking about?
So yeah, so this is MPI. So all of these all of these ranges of cores are with MPI, and then the implementation works with multiple GPUs communicating with MPI, but I haven't tested the speed up yet.
Oh, okay. Now, even with a single CPU or a node, you potentially can have some kind of a hybrid. OpenMP, shared memory, whatever. Have you used any of that, or this is a pure per core, per RAM? Then you use the MPI between different cores.
Yeah, just using MPI between different cores is what this is testing.
Oh, okay. Thank you for the clarification.
But all of in all of these cases, these were all sitting on a single compute node. So it was on a compute node with 128 cores. And so I just used what was available there to kind of minimize the communication like overhead.
Okay. By the way, when you use the GPU, you are using the CPU to moving the data, right? To do the coordinations, whatever.
I guess so, yeah. So it's kind of I guess if the compiler is aware of both the GPU and MPI, then it can, I guess, do some optimizations of that. But I'm not sure if that's
Thank you.
already in there. Yeah.
Yeah.